Hey guys, so we're starting on section 4.3. Piggybacking on what we just did in 4.2, which was the natural exponential function. We covered exponential functions in general, which are functions with a base that is a number and a power that is a variable. Then we sort of in 4.2 brought in this new concept, which is a function that has a base that's a number of 2.718 that has a power of x, or e to the power of x. Now in 4.3 we're gonna work a little bit backwards. So right before we broke off, we did discuss inverse functions, and we'll see that our standard exponential functions, like y equals 7 to the x power, for instance, would have an inverse. So where I'm at now in our slides, we're covering section 4.3, which are logarithmic functions, slide number 75. In the last section we saw exponential functions that were similar to this, y equals 7 to the x, for instance. Now in 2.8 we learned about inverse functions. And the concept of inverse functions where we take a rule and we find the reverse rule. So if I had a rule that mapped an input 7 and I f'd 7 to get an output 11, we discussed how we can find the inverse of a function to take that output 11 and map us back to the input, which is 7. So if we f inverse 11, we'd get the original input value of 7. So we can use this concept of inverse rules to say, okay, a forward rule will map me from x to y. The backwards rule should take me from y back home, back to x, back to where I came from. With exponential functions, the variable is in the power. We have logarithmic functions that are going to be used as an inverse to exponential functions. What does this mean for us? So, if I say the inverse of an exponential function is a logarithmic function on my slide deck, let a be a positive number, a is not 1. The log function of base a, denoted by log base a, is defined by, and then I have a definition. Log to the base a of x equals y implies that a to the y power equals x. So if a to the y power equals x, that means log to the base a of x equals y. What a log function asks us to do is it asks us to please tell me what the exponent is. What power do I need to bring a to in order to get x? A needs to be raised to what power? To the y power to give me x. Now in your slides, and it shows you as a is the base and y is the exponent. In your slides, I have a box that says remember me. So this might not be so appropriate for YouTube, but as many of you know, I really don't care. My job is to help you guys learn this stuff to the best of your abilities. And I know that with most of my college students at QC, there's only one thing on your people's minds. So one way that I think about this in order to help me remember, I guess, this rule is the following way. Instead of log to the base a of x equals y, I say log to the base s of e equals x. Sex. Log to the base s of e equals x would mean s to the x power equals e. Sex, sexy, right? And whoever said that math can't be sexy or good looking? So log to the s of e of x could be s to the x power equals e. One way to remember it. Not the cleanest way in the world. I forgive those of you, or please forgive me, if any of you have the cleaner mindsets. But unfortunately, this is one way that tends to stick in your mind. So let's see this in action. Okay, what does this rule necessarily mean? Again, if I have an exponential function and I need to solve for a variable power, what I'm saying is we can use this weird log stuff to solve for that power. First, we need to get comfortable with the notation. We're going to have a few sections on logs, so don't be so concerned if you don't get this automatically, but let's work through a few problems and hopefully we'll get through the hang of it. Log to the base a of x is the exponent that I need to raise a to give me x. So if I have log to the base 10 of 1,000, what this is telling me, or asking me rather, is 10 to what power? 10 to what power would give me 1,000? The answer is 10 to the third power gives you 1,000. So the answer would be 3. So log to the base 10 of 1,000 would be 3. Another problem, log to the base 2 of 32. Log to the base 2 of 32. So again, what is this asking us? This is saying 2 to what power? 2 to what power would give us 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 5. 2 to the 5th power is 32. And so on and so forth. Your slides have another problem. Log to the base 16 of 4. So log to the base 16 of 4. So this one looks a little weird. 16 to what power gives me 4? 16 to what power would give you 4? Well, the square root of 16 is 4. And the square root, when we discussed exponential powers and rational roots, we said 16 to the 1/2 power is the same as the square root of 16. So the exponent needed, 16 needs to be raised to the 1/2 power to give me 4. And that's basics on how log functions work. That's slide 75. Slide 76. So we saw, and here this is going to be a little bit more theoretical, we saw that we had inverse function properties. F of f inverse of x is x. F inverse of f of x is x. Which just means, again, from 2.8, when we apply a forward rule and a reverse rule at the same time, you really just get stuck in the same place or wherever you started. It doesn't matter if I'm applying a forward rule and a reverse rule, or a reverse rule then a forward rule. It's like me taking a step forward and then a step back, or a step back and then a step forward. You're still going to end up in the same place. So what this inverse function property tells us is, if I take the log of the exponential function, or the exponential, or the log of an exponential function, so we'll see it all worked out here. If f of x is a to the x, and f inverse of x is log to the base a of x, we see that log to the base a of a to the x, so it's like saying if I take the inverse rule, a to what power gives me a to the x? The x power. A to the x power gives me a to the x power. And also, a to the power of log to the base a of x is x as well. These two rules I wouldn't really stress. I don't think they're anywhere near as important for now in this context. The theory behind it is important though. When we're going to discuss in later sections how to solve exponential functions and how to solve logarithmic equations, we're going to have to understand the logic. And the logic is telling me if I take the log of an exponential function, I'll just get the power. So this is going to be useful when I try to find x or when I try to solve for x. When I take the when I raise a log function to a power, I can also find x, which again is going to be very useful for us in later sections, but we're going to see applications of this that help us understand it better and make more sense. For now, I'm going to move along to the other properties on the slide. 1. Log to the base a of 1 is 0. So log to the base a of 1. Well, a to what power would give me 1? A number to what power gives me 1? 0. 7 to the 0, a billion to the 0, a trillion to the 0, anything to the 0 power gives you 1. So if a is any number, a to the 0 power gives you 1. That's the first property. Second one, log to the base a of a. Well, a to what power gives me itself? A to the first power. A to the 1 equals a to the 1. And then 3 and 4 are piggybacking. So log to the base a of a to the x is x, and it's basically here. These two. These are 3 and 4. That again, we're going to discuss more in depth later on, but they make sense. They're using the inverse function property. Okay, definitionally, on the same slide, a log with base 10 is called a common log. So, if you see something written as follows, the log of 100, don't think, oh, they forgot to write the base. This has to be a base to some power gives me this value. The base isn't missing there. That's done on purpose, notationally. Whenever we have a base of 10, we just don't write it. It saves you it's a shorthand, it saves you time. So log to the base 10 of 100 is the same as log of 100. And actually, if you guys bump this into your graphing calculator, you'll see the log function right here, right? This button, log. So you notice that it doesn't have a base. So if you do log of 100, right? The log of 100 and you hit enter, the calculator thinks that it's the log of base 10. So 10 to what power gives me 100? And that's what it's answering. 10 to what power? What power do I need to raise 10 to give me 100? That's the second power. So if we ever omit writing a base, it's called a common log. So how would we evaluate that I have here? We have log of 100, that's 2. How would we evaluate the log of 50? So far we've only really gotten clean requests, right? But how would I get log of 50? This is asking me 10 to what power gives me a 50? Doesn't really make sense. 10 to the first power is 10, 10 squared is 100. So it has to be something between 1 and 2. It's not a whole number. Well, are you going to sit there and plug and chug away all day? 10 to 1 is 10, 10 to 2 is 100. It's between 1 and 2, so what's 10 to the 1.5? Oh, that's not 50. 10 to the 1.4, oh, that's not 50. That's not really how we play it. We're just going to plug this into our calculator. You can do log of 50, and you get 1.698. So the log of 50 is equal to 1.69, or 1.7. So just like we discussed common log, on the next slide we're also going to briefly touch on natural logs. Just like we had the natural exponential function, which was an exponential function that had a base e, f of x equals e to the x, right? That was a special scenario or a special case. Here we're also going to discuss the natural log. So for the common log, when we have a base of 10, we don't write it. If we do log to the base of e of x, we're going to convert that to just say the ln of x. And you could find the ln of x right under the log of x button on your calculator. Here you have log, here you have ln. Okay? So don't be confused. If you ever see something like evaluate the ln of 4, they're asking you to say, well, log to the base e of 4, which means e to what power gives you 4. They're asking you to evaluate what exponent do I need to raise e to get 4. And again, your calculator can solve this. You can hit ln and ln of 4, which gives you 1.386. So e to the 1.4 power roughly gives me a 4. So again, what's the relationship? The ln of x is y, e to the y is x. It's on the slide. But how are we connecting log or ln? If you see an ln of x, don't be confused. All the ln is another way of saying log. It's still an inverse exponential function. They still want you to find the power. I still want to know what power I need to raise e to in order to get this value x. So the ln of 4 is still log to the base e of 4. It's just a different notation, a different way of writing it out, instead of having log to a specific base. The properties of natural logs are very similar to the properties of the standard log functions that we just had. You'll see that log to the base e of 1 is 0. Because e to the 0 power is 1. This is again asking, e to what power gives me 1? E to what power gives me 1? Well, e to the 0 power gives me 1. It's asking for the exponent, and we solve for the exponent. Log to the base e of e. Well, this is saying e to what power would give me an e? So the answer is 1. Log, and again, in your textbooks they might have, instead of log to the base e, they might say ln of 1. They're equivalent. Instead of saying log to the base e, it might say the ln. Instead of saying log to the base e of e, it might say the ln of e. So the ln of e is 1. And the next two are based off of the inverse property rule, log to the base e of e to the x, or ln of e to the x. So again, if we apply a reverse and forward rule at the same time, we should just get x. Ln of e to the x is x. And e to the log to the base e to the x equals e to the ln of x, which again equals x. These two are based off of the inverse function property rule, that if I apply a reverse and a forward rule, or a forward and a reverse rule at the same time, they cancel each other out. So that's all we had in 4.3. What is to come? This section just gave you a broad definition on what logs are. Again, what logs are meant to do are, they're meant to give you a tool to work backwards. If you had an exponential function, how can I solve for that exponent? Right now, you'll see homework problems in 4.3 that are mainly definitional in that regard, and you can use your calculators to solve for many of them because you have to evaluate, let's say, the log of some value to some base. If the base is not a standard base, some of your calculators may be able to hack, let's say, a log to the base of 4 or a log to the base of 5. Anybody with a TI-83 plus might not have that functionality. So I'm not going to show you those hacks on this calculator. It's not fair. We are going to get a log base formula in sections that are to come. So in 4.4 and 4.5, we're going to get some laws of logarithmic functions. Those laws are really going to help us manipulate logarithmic equations and exponential equations in 4.5. So all of 4.1, 4.2, and 4.3 are meant to do is sort of prepare you for the mayhem that is to come in 4.4 and 4.5. So what you were supposed to get, at least from 4.1 and 2, were basics on exponential functions. Our base is a number, our power is an exponent. How does that make the graph look different? How does that affect the function? And in this section, introduce you to logs, which are the inverses of exponential functions, which are supposed to tell us, okay, if I have an exponential function, how do I work back to solve for the exponent? Or if I'm given, let's say, a log to the base 4 of 64, what am I really asked to solve for here? Here I'm asked to solve for, well, 4 to what power gave me 64? I'm asked to solve for the exponent. Okay? So we're looking for that power. The log functions are the reverse. They're taking the input, right, of the base and the result. So they're taking the result as the input to map you back to see what that output was. The initial input was. For the exponential function, so let me just make a small chart to clarify. The exponential function, let's say, is 4 to the x. My input values would be values for the variable or for the power. So if I had a 3, 4 to the third would map to 64. What the log functions are meant to do is say, hey look, if 64 now is my input, what is my output going to be? A 3. That maps me back, right, to where I started from. I started from an input value of 3 in y equals 4 to the x. So the exponential function works one way, the logarithmic function works the other. And we're going to be able to, or we're going to be exposed to new rules or laws that are going to help us manipulate log expressions and also log equations and exponential equations. That'll hopefully help you guys in calc. Stay tuned and let me know if you have any questions.